would have to usually say you're okay with it. Okay, so perfect. Now, so last time, so this Ringvorlesung is, about giving you some idea about non-commutative geometry, about the objects that we work with, and about the general idea. I just want to sort of convey to you the general idea of non-commutative geometry. And so let us recap what we did and what we formulated last time. Sorry. Right. So in the recap, non-commutative geometry, I said we want sort of a distance or a distance notion that is independent of points. So points. So it's more in a spirit of quantum mechanics, right? Where I told you quantum mechanics, there you don't have points, you don't have a usual phase space that is replaced by a Hilbert space. The functions are what usually is your energy function or your momenta or your coordinates are replaced by some operators. Usually they are, in the context of quantum mechanics, self-adjoint operators, and therefore they have real eigenvalues. So the spectrum is real, okay? And that is sort of the main difference between quantum mechanics and classical mechanics, and this is sort of the spirit of non-commutative geometry. And last time we went through the distance function. So the distance function between 2 points, let's say P and Q, or 2 states in that sense, is the supremum of a function that is C1 of R, for example. And we take the absolute value of omega P of F minus omega Q of F, where omega is some linear functional, and with the additional restriction that the derivative of F has to be less equal than 1, which equals then, if you replace functions by operators, that the commutator of this function that can be understood as a multiplication function on some Hilbert space, that is less equal than, so the commutator of that with the dx is less equal than 0. And last time, as a sort of a teaser, I also explained to you the concept of the spectral triple, right? So sorry, I don't really see the chat here. So if you have any questions, I think audio would be best, so I don't need to keep switching here. And then, we went on to define what a spectral triple is. You have a C-star algebra acting on some Hilbert space and a self-adjoint operator D with a compact resolvent. And as I said, we defined the resolvent as, so C modulo the spectrum of this operator, such that the commutator of D with A, so this operator, it's most cases the Dirac operator, is bounded for all A element in the algebra. I will repeat a little bit, last time we did it in more extension, but let me repeat here again. And a C-star algebra is a norm-star algebra, which means it's an algebra. As I said, an algebra is basically you have elements of some set, and you know how to multiply and add these elements such that they remain in that set. A star algebra is an algebra that has an involution, so some star. So A star star is equal to A, and so on. It had these nice properties. A norm star algebra is a star algebra that has a norm in addition, and that is complete under the norm. That is then called a Banach star algebra. And if it satisfies the norm of A star is equal to A, and A star A is equal to A square for all A element A. And I gave you examples last time. The function space of continuous functions on a compact manifold. Okay, so in the compact case, you only need continuous functions. That already gives you a nice C-star algebra where the involution is basically just the complex conjugate. And for the case that M is non-compact, you need to define some boundary values for the functions. Okay, you say, okay, we take the functions that vanish at infinity, or the continuous functions that vanish at infinity. And right, and another example, which is one of the most important examples in a sense for physics, and in this context of C-star algebras, is the space the Hilbert space of all bounded operators. Okay, what is a bounded operator? So you have here a norm. The norm is given by the supremum norm, and the bounded operator is such that the supremum norm is just less than infinity. So this is just a number, it exists. Okay, these are bounded operators. Now, last time I was not that very precise on this definition, so I will give it again. A star morphism between two C star algebras A and B is any C linear map, mapping the C star algebra A to the C star algebra B, that satisfies P of AB is equal to P of A times P of B, and P of A star is equal to P of A and the whole thing starred. Okay, for all elements of AB element A. So it's a morphism, so there's a star morphism, and if it's in addition a bijective as a map, it's called a star isomorphism. You can easily prove basically that the inverse map is automatically a star morphism. So I think Johannes pointed that out last time, if I'm correct. And then, moreover, what you can also prove is that if you have some element of an algebra that is positive, then, if you have a star morphism, then the map of this element will also be positive. And the proof is very nice, actually. So, I told you last time a little bit how interesting C-star algebras are, but I didn't have the feeling that I really, gave you another information why it is so interesting. So maybe this will help a little bit. So the proof is basically very simple. If A is greater or equal than 0, then A can be written as a product of B star B for some random element B in the algebra. And now, since we have a morphism, a star morphism, P of A can be written as, so A is B star B. So P of B star B is equal to P of B star times P of B. And this is equal to P of B star, which basically gives you like the norm of something squared. And that is always bigger than 0 for the case that you have a norm, of course, which is the case here. Right. Now, I think that I gave you as well, but I try to recollect a lot of things that we did last time so that, in a sense, this Ringvorlesung becomes also a little bit more clear. A representation of the C-star algebra A is a pair, H and pi, where H is a Hilbert space and pi is some star morphism that maps, the algebra to the space of bounded operators, the C-star algebra of bounded operators in that Hilbert space. The representation is called faithful if the kernel, so the null space of this representation is the 0 space. And now, okay, this is not really the subject that we were talking about, but it all has sort of an equivalent importance in it. And I thought, why not just tell you about some interesting stuff as well that doesn't necessarily have to do with that. So an arbitrary C-star algebra A, so there is this GNS theorem by Gelfand, Naimark, and Siegel, which says that an arbitrary C-star algebra is isometrically star isomorphic to a C-star algebra B of H. Okay, so you can always map any C-star algebra, any abstract C-star algebra, given with a norm and all that, to the C-star algebras of bounded operators on a Hilbert space. That is why B of H is such an important space to study. And isometrically means that the norms are also equal. And the significance here is that it allows you to consider C-star algebra as an abstract entity without reference to any particular realization. You can work with it, you can prove some nice things or whatever you're doing with it, and then you can always, map it to the space of bounded operators. And that is a very strong statement. And of course, some Russians have to prove it, but it's really, okay, Siegel is not Russian. And there's a commutative version of that because, an arbitrary C-star algebra is not necessarily commutative, right? So the elements of this algebra, A and B, AB is not necessarily equal BA. But in the case that you have a commutative C-star algebra, one can reconstruct a host of topological space M such that A is isometrically star isomorphic to the algebra of continuous functions on that manifold. And this is really mind-blowing in a sense because, you have something very abstract, which is an algebra, right? You have a commutative C-star algebra. And from that, basically this theorem tells you that you can construct something as a host of topological space, which has some geometrical entities in it and so on. And it maps you to the algebra of continuous functions on that manifold. But what manifold? We were not even talking about one. And now all of a sudden, you know, you have a commutative C-star algebra with a very abstract entity, and that can be mapped, you know, to something on a manifold. And that is sort of, you know, also a little bit the spirit maybe of non-commutative geometry, if I may oversimplify it. Another nice theorem that I want to tell you about is the GNS reconstruction theorem, which has, you know, tremendous significance in physics, and especially in quantum field theory, which is the theory of quantum mechanics, of relativistic quantum mechanics in a sense, but considered for infinite many particles, if I may oversimplify it. And in there, it tells you, you know, any state omega, okay, in a linear positive functional actually, so that maps the algebra to C, induces a Hilbert space representation called the GNS representation. So you're working with an abstract algebra, right? All the time, you prove some nice stuff with it, and now you need to go to the real world, as we call it, and do some measurements, let's say. And for that, you have to, you know, represent these abstract entities as something, you know, that can be related to a scalar product or something of sorts. And so given this C-star algebra, then you have, you know, some state omega. You can construct a Hilbert space, a representation of this, you know, C-star algebra by bounded. So it's a representation of A by bounded linear operators on HW and omega W. Okay. Now omega W is just a unit vector in HW, and omega W is cyclic for pi W, which means if I map PW of A omega or act with it on omega W, it is dense in HW, which means if I take the closure of that, it's H. And the state is basically the scalar product, or the, what do you call it? Yeah, the scalar product, bracket notation, if anyone is familiar with that, of omega W, pi W of A, and omega W. Okay. And the real challenge in that from a physical perspective, especially when it comes to quantum field theories on spacetimes that are curved, so that are not flat as Minkowski space or Euclidean spaces, for example, is to find such a state, right? And there is a huge, you know, amount of thought that is put into that, but that would, unfortunately I could not. I mean, one could give a whole Ringvorlesung about that. Okay, now, in a sense, what I want to do at the end of this lecture, well, maybe not today, but the next time, is, so I gave you last time sort of this very abstract definition of a spectral triple, right? And I want to show you how you can have an algebra, a Hilbert space, and some sort of operator, separate joint operator that has compact resolvent and so on, and how you can reconstruct geometry from all those three things, okay? And this is sort of what I mean, not what Kohn did way more, but this is, you know, on the heart of what is also used in physics, of that what Alan Kohn did for non-commutative geometry. I mean, yes. So what I want, one of the very important entities that we work with is the so-called compact operators, okay? I will define what a compact operator is. So first of all, recall from linear algebra, for example, that an operator on a Hilbert space has finite rank if the orthogonal complement of its null space is finite dimensional. Okay, so the dimensional of the kernel of the orthogonal null space is finite dimensional. Intuitively, that means intuitively it is as equal to a finite dimensional matrix in an infinite dimensional Hilbert space, right? And so an operator on a Hilbert space is said to be compact if it can be approximated in the norm by finite rank operators. So for all epsilon bigger than 0, there exists a finite dimensional subspace E, that is a subspace of H, such that the norm here restricted to the orthogonal complement of E is less than epsilon. And we denote the set of all such operators as K of H, so the set of compact operators, which is a subset of the bounded operators. Sorry, I have a small problem here. Okay, so is it clear as far as now? Perfect. Right, okay. There are a lot of equivalent definitions of a compact operator. I will give you as many as possible in order to confuse you as much as possible, or also to make it a little bit more clear, because this notion is very important. And I mean, in a sense, if I would, I mean, gun to my head, and I would try to say it as simple as possible, a compact operator is an operator such that you take some bounded sequence, which is of course not necessarily convergent, and you apply the operator on this bounded sequence, and this bounded sequence becomes a convergent sequence. Okay, that would be like the very, you know, simplified version of what a compact operator is. And I mean, this is all hidden in the definition. So an operator is a compact operator if the image of each bounded set under T is relatively compact, which means the closure is compact. Equivalently, if T is a map from X to Y, it is called compact if and only if it maps bounded sequences in X to sequences in Y with convergent subsequences. Another equivalent definition is the following one. An operator T on H is called compact operator if it can be written as the sum over lambda n bra fn ket gn, with fn and gn being orthonormal systems, not necessarily complete, and lambda n being a sequence of positive numbers with limit 0, usually called the singular values. And what is interesting is so in this bounded business, so sorry, let me just write here something. So in this bounded, I don't know why this guy is doing this right now. Sorry, let me just restart this. Okay, so make here. So you have the bounded operators, right, on the Hilbert space. So these are operators that have a finite supremum. Now, a subset of those are compact operators. So compact operators are bounded operators that fulfill additional properties, right? And there are also operators which are called the trace class operators. So Hilbert-Schmidt norm, Hilbert-Schmidt class operators. And basically in those operators, you can take the trace. Okay, for example, let's take a matrix on a finite dimensional space, 2-dimensional 1, 2, 0, 0, and 3. I mean, even as easy as possible, right? And the trace of that matrix is 5, okay? And thus, you know, this matrix considers an operator between two Hilbert spaces, let's say C2 to C2, has a finite trace, and that is a trace class, okay? Of course, when you work on infinite dimensional Hilbert spaces, a trace does not have to exist, because, I mean, take 1, 0, 0 everywhere except for the diagonal, and that's all ones, but that goes infinitely long. You take the trace of that, that's, you know, doesn't converge to any number, right? And so this is still as another special class of bounded operators. Just wanted to mention that in the going sort of. Now we come to the quantized calculus, and that's why I explained to you right now what the compact operator is, because it plays an important role in the definition of the quantized calculus. So this image is taken out of Con's book about noncommutative geometry. So I don't know if maybe I shouldn't ask that on camera, but does anyone not know Alan Cohn? Because I'm using his name as if everyone is familiar, which, I mean, you're still students, you don't have to know everyone. So everyone is familiar with the name Alan Cohn. I mean, he's a field medals winner and everything. I mean, it's a big shot. And there's nothing to say in that direction. And I mean, he basically, you know, did noncommutative geometry, or you know, founded that subject and made it mathematical as precise as we have it right now. And in his book, basically, he writes a class in classical mechanics, you know, or in classical theory. We look at so you have some complex variable, which usually physicists would associate functions with it, right? These are some functions, functions that describe some, you know, physical quantities. And in quantum physics, you replace those functions by operators in H, so acting on this Hilbert space. A real variable, okay, because I mean, in general, you can have operators that are not self-adjoint, right? I mean, but in essence, in physics, since at the end of the day you want to have something like a real number, so a real variable corresponds from the classical side to quantum mechanically to a self-adjoint operator in the Hilbert space. And now, so you see, we go through the list and we try in this classical calculus manner, we try to replace every classical concept with something, you know, on the quantum side, whatever that means now for the time being. And in infinitesimal can be pretty good approximated or replaced by the notion of a compact operator. So these operators that I introduced to you right now, so if you have, you know, if T is a map from X to Y and X has bounded sequences, then T of X has some convergent subsequences. Okay, and now another important concept is an infinitesimal of order alpha. So when you do, I don't know, derivatives, for example, or integration, you always have these infinitesimals in there. And they are replaced here by compact operators on a Hilbert space whose characteristic values, mu n, satisfy the following. Mu n goes as the order of n to the power of minus alpha, so a compact operator of order alpha, is such that the characteristic values go as n to the minus alpha if n goes to infinity. I will give a more precise definition in a second, but I just want, I found this picture very, very nice in a sense, just to get an overall perspective of what is happening. And the differential of a real or a complex variable is given by this sort of df. I will hopefully next time also define exactly what a d is in that case. So it's a derivation. It satisfies the Leibniz rule and so on, and it's not nilpotent. And you can write the differential as some commutator of some operator f, which we usually call d, so the Dirac operator, for example, with a function f, or an operator f in that sense. So, I mean, function and operator, because it's a function, if you apply it to f of x, this is f of x psi of x, where sort of f is a function of multiplication operator with respect to these functions. So that I already told you about last time. And then, you know, before we go, an integral of infinitesimal of order 1 is given by the Diximir trace. I will also define what the Diximir trace is and give you examples of what this is. But you see, in the quantized calculus, we replace all these classical quantities, classical calculus quantities, with quantum ones. And how this is done, I will tell you in a second. So far, any questions of where we're going, or Perfect. Okay. Let me close everything. Good. Now infinitesimals. Before proceeding, we arm ourselves with a few results. So one proposition is let us have a compact operator, then its spectrum is a discrete set having no limit points except perhaps lambda equal to 0. Furthermore, any lambda unequal to 0 is an eigenvalue of finite multiplicity. Okay, that is maybe not important. The most important thing is for compact operators, their eigenvalues, or by the eigenvalues, their spectrum is a discrete set, right? And the next proposition says if you have a compact operator and it is self-adjoint, then you know there exists a complete orthonormal base, phi n, where n goes for all the natural numbers, for H such that T phi n is equal to lambda n phi n, and lambda n goes to 0 as n goes to infinity, right? Because it's a compact operator, basically. Okay. So for example, a very nice example for some sequence of compact operators, e to the minus n squared, okay? N squared being, you know, an element of the numbers or something. On the natural numbers, for n goes to infinity, you see this whole thing will take, you know, a lot of convergent sequences, you know, on some subspace and map bounded sequences and map into convergent sequences, right? So a very nice example, which we like to remind ourselves in is e to the minus n squared. Right. So another proposition says the following: if T is a compact operator, it has a uniformly convergent representation with respect to the norm, which is given as T equal to mu n of T psi n phi n, where the mu's, you know, they're bigger than, greater equal than 0, and mu j plus 1 is less equal than mu j, and psi n and phi n are orthonormal systems, not necessarily complete. And the idea here is the following. So any operator has a polar decomposition, so you could decompose it in u, some unitary, and t, which is the mean value of t, and then mu n of t goes, so or mu n goes to 0 as n goes to infinity. So these are the eigenvalues of this compact operator, and phi n are the eigenvectors of this self-adjoint compact operator, and psi n is u phi n, okay? So this is sort of the idea why I can write any compact operator in this way. And this will become important, okay, in a second. Sorry. So for any alpha that is r plus, the infinitesimals of order alpha are all compact operators such that these eigenvalues or singular values mu n of t are of order n to the power of minus alpha as n goes to infinity. So there exists a C such that mu of t is less equal than this constant times n to the power of minus alpha for all n bigger than 1. Okay, so this is what makes an operator an infinitesimal of order alpha. And of course, you can see that you know, mu n plus m of t1, t2 is less equal than mu n of t1 times mu nu of t2. Oh, sorry, that should be an m. And okay, orders of infinitesimals behave well. So this is basically what is important in here. So again, you have compact operator. You can do this, you know, decomposition that I showed you here of this operator by using the polar decomposition. And now the singular values or the characteristic values, mu nu of t, have a certain, how do you call it, a certain asymptotic, you know, as n goes to infinity, and that is of order a to the minus alpha. For example, if some operator, if these n of t for the limit n goes to infinity go as 1 over n, then you have an infinitesimal of order -1, okay, and so on. So of order 1, right? Because I mean this is n to the power of -1, and 1 is alpha. So, and this is sort of why this is important. These are the infinitesimals that we're going to study. We're going to study all compact operators such that they are infinitesimals of order 1. So, and the point is that the trace of those operators does not necessarily have to converge, right? For compact operators, because they're not necessarily traceless. But we need to take something like a trace in order to replace this idea or concept of integrals. And for that, there is a construction, or there's a trace called the Dix-Meyer trace. Sorry, I always write his name with the I. It's the Dix-Meyer trace. And this trace is constructed such that infinitesimals of order 1 are in the domain of the trace, and infinitesimals of order higher than 1 have a vanishing trace. Okay, so in a sense, it is similar to the integral where you neglect certain orders. This is what the Dix-Meyer trace does. It defines, in a sense, a trace of compact operators that are infinitesimals of order 1, and for those that are higher than 1, it vanishes. So you have the usual trace here given as, you know, with some orthonormal systems, psi m, psi n, and it's called L1. And if t is equal to k of h and t bigger than 0, then nu of t, then this is just the sum nu of t, which is, you know, these singular values. But this does not necessarily have to converge, and this is not appropriate for the upcoming purposes, and thus we define this so-called Dix-Meyer trace. So for positive infinitesimals of order 1, the usual trace is at most logarithmically divergent. Okay, so if you take the sum over that, it is, you know, it goes, because it's of order 1 of n, it goes as 1 over n, and if you take the sum over that, it behaves as ln n. So as the logarithm. So in a sense, we know how bad it diverges. It diverges at most logarithmically. So all, you know, the compact operators, positive infinitesimals of order 1, they can, you know, worst case scenario, the trace diverges logarithmically. And thus, the Dix-Meyer trace is a trace defined in such a way that it extracts the coefficient of the logarithmic divergence. This is maybe like the most sensible way to state it. And and now let's define L of 1 infinity. It's the ideal of all compact operators, which are infinitesimals of order 1. And if T is L1 infinity, is positive definite, then we can define positive functional as a limit of cutoff functions or cutoff sums as the following. You see, because as I said, this, you know, can be just worst case scenario ln n. So this thing, it can only be less equal than c ln n. You divide by the logarithm of n, and then you take the limits. This is how you define the trace. In a sense, this is sort of the sensible way to do it. But there are two problems with the previous formula: linearity and convergence. Okay, so not in general, this looks like that. And so we define gamma n as the sum over all these singular values divided by the logarithm n. And it satisfies the following. So sigma n of t1 plus t2, so the sums over these singular values, is less equal than sigma n of t1 plus sigma n of t2 for all t1, t2 that are element of these compact operators, and sigma of sigma 2n, okay, of t1 plus t2 is greater or equal than sigma n of t1 plus sigma n of t2, and for all t1, t2 that are positive, and hence in turn for any two positive operators, you have this inequality. So gamma n of t1 plus t2 is less equal than gamma n of t1 plus gamma n of t2, and then you use the second one, and then you have gamma 2n of T1 plus T2, 1 plus ln2 divided by ln n. Okay, this is just an inequality. So in a sense, this cutoff sum that we defined, right? So this ln n sum over 0 to n minus 1 of mu n of t, right? That fulfills certain inequalities, and you see that for n goes to infinity, this term goes to 1, and this becomes basically equal to this one, and thus it is linear and convergent. So from linearity follows convergence. From convergence, linearity follows. In general, however, these sequences gamma n, okay, this one does not have to converge, okay? They do not have to converge. And but there is a way to make them convergent in a sense, and that's what I'm going to explain right now. So take the eigenvalues gamma n of t. They are unitary invariant. Why? Because in a sense you have gamma nu of t, and you have the sum here, and this is equal to gamma nu of u t u inverse for unitary operator. And thus the gamma n's are as well, okay? And then one obtains a unitary invariant positive trace on the positive part of these compact operators that are infinitesimals of order 1 for each linear form lim w on the space L infinity of n of bounded sequences. And they satisfy certain properties. In the end, so scale invariance may be important here, and if gamma n is convergent, this limes with respect to this linear form becomes just the usual limit, okay? But it's not in general. But you can, basically we will show that it is independent of omega, so don't stress that point too much. What I would like to stress is that Dixon proved that there exists an infinite family of such scale invariant forms. Associated with it, there is a trace, okay? And this trace is basically exactly the thing that I gave you before for all t that are positive and for all t that are compact operators of order 1. The interesting thing about this new trace is it is additive on positive operators. So if you take trace of t1 plus t2, this was equal to trace of t1 plus trace of t2. So this is not necessarily trivial. I mean, the usual trace satisfies this linearity, but I mean, if t's are bounded, trace class operators actually, but in general, this does not have to be satisfied. And moreover, the trace of this operator is greater equal than 0 if t is greater equal than 0. And the trace of lambda 1 t1 plus lambda 2 t2 is equal to lambda 1 trace of t1 plus lambda 2 of trace of t2. So this linearity with respect to some constants, sorry, this lambda 2 is element of C. And the trace is cyclic. This is very nice actually for all bounded operators. So you have t, which are compact operators that are infinitesimals of order 1, and the trace, so b times t is equal to t times b, and the trace is 0 if t is of order higher than 1. And this is what this trace sort of does, okay? So this trace is defined for compact operators, even though they are not necessarily trace class. So there's a trace defined for compact operators that are not necessarily trace class. In addition, if these infinitesimals have an order higher than 1, this trace vanishes. Okay. Good. Now, let me give you an example. I know this was like a lot of, in a sense, blah, blah. But let me give you a very nice example. Powers of Laplacian of an n-dimensional flat torus. Okay, you have flat torus, S1 cross S1, n times, and you have the Laplacian of that torus. Okay, so that is d squared dx1 squared plus blah, 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 d squared dx squared n. And that has some eigenvalues. I mean, this is just standard sort of torus knowledge. And that the eigenvalues are Lj, so the square or the norm Lj square, where Lj's are all points of the lattice Zn taken with multiplicity 1. Now we want to see what does that mean for the case that we take the Laplacian to the power of s. That means it has eigenvalues Lj to the power of 2s. And now for the Dixmuir trace, we need to estimate this product, right? And then take the sum for n goes to infinity and see, in a sense, when does this converge, right? So, okay, here it's done in this way. Let nr be the number of lattice points in the ball of radius r centered around the origin of Rn, right? Okay, and then you can approximate this nr by the volume of this sort of unit ball, and nr minus dr minus nr is equal to omega n, where omega n is the area of unit sphere of Sn minus 1. And in the end, you get that the sum L to the 2s can be approximated, okay, by the integral of 1 to infinity of r to the power of 2s, nr minus dr minus nr. And so this is just yeah. And now you know that this is omega n Rn plus 1. You insert that. And now you have the integral of 1 to infinity of r to the power of 2s plus n minus 1 dr. Now, for the logarithm of nr, this can be approximated by n log r as r goes to infinity. So now you see, we basically pretty much, you know, wrote this term and this term, now the product. So you can see, you know, from this integral, okay, I mean, this is just a volume, area of unit sphere, so just some number. But here the point is, if s is greater than minus n half, this r has, you know, a positive exponent, and thus, you know, from 1 to infinity, this whole thing diverges. Now, if this is less than minus n half, this goes to 0. Okay, and if s is equal to minus n half, it goes as log, and then you can divide it by the log r, and thus it goes as omega n divided by n. Therefore, the sequence gamma n of this operator of the Laplacian to the power of s on this torus diverges for s greater than minus n half and converges for s equal to minus n half, right? And converges for s less than minus n half, but there it goes to 0. Thus, this Laplace operator on the torus is an infinitesimal of order 1 with the trace omega n divided by n, okay? And with the Dixmuir trace, okay? And this is what the Dixmuir trace does. Now, another example, powers of Laplacian on the end. So basically take a Laplacian or take some operator of which you know the eigenvalues, then, I mean, and right, okay, you have also to prove that this operator is a compact operator, but that is another discussion. So the Laplacian operator on the sphere, on the n-dimensional sphere, has eigenvalues L times L plus n minus 1, right? So for the physicists, so 3 minus 1 is 2, that doesn't make any sense. Let me look at it. So, I mean, usually you have, you know, the orbital momentum algebra, and it has L times L plus 1 eigenvalues and so on. But okay, the point is, you know, the Laplacian operator delta on Sn has these eigenvalues with a certain multiplicity. And, you know, L is element in n, and in particular, M0 is equal to 1, M1 is n plus 1, and so on. And one needs to estimate as n goes to infinity the sums. Right, log L to infinity, L0 to n, ml, and you know, 1 over the whole thing as well. 1 over the logarithm of n. So basically, these two sums are really what is important right here, right? So because you will at the end take the product of those two sums. Basically, it's a long calculation. I mean, we can go through it. I don't think it's very productive in a sense. Basically, the sum here is 2 times n to the power of n divided by n factorial, for which the logarithm L equal to 0 of n ml is approximately logarithm of n to the power of n plus log 2 minus log n factorial. and this is approximately n log n. Similar for L equal to 0 to n ml times L plus n minus 1 to the power of minus n half. That goes to 2 divided by n minus 1 factorial log n. Now you divide those two, and you take, so you divide those two, and then you take the limit, and this goes to 2 divided by n factorial. Okay, so you see again, we had a compact operator, not necessarily trace class, not trace class at all, actually. And now we had this, you know, Dixit trace, which was a way to extract, you know, because you see, I mean, if we wouldn't have this one, this thing blows up in your face, right? So if we wouldn't have the logarithm of n, and thus this Dixit trace is defined for the Laplacian on the sphere as 2 divided by n factorial, where s is equal to minus n half here. Just need to check the chat if anyone still have questions. Okay. So let me give you another example. It's a very nice example which we physicists pretty much love, is the harmonic oscillator. Okay, so the harmonic oscillator, so the Hamiltonian of the one-dimensional harmonic oscillator, the Hamiltonian in a sense is an operator that is the operator representation of the energy. So there are the, I mean, just to put it in a more simple way, there is sorry. Okay. There is, you know, H psi equal to E psi. So I mean, and this is equal to I d dt psi, which is the so-called Schrödinger equation, and this is an eigenvalue equation actually for the harmonic oscillator, or you can also do it for the hydrogen atom, for example. Okay, and you know, it's a solvable integrable model, and this is why we love the harmonic oscillator. And in one dimension on the Hilbert space L2 of R, so all real functions that are square integrable, its eigenvalues are basically n plus 1/2. Okay, you can see that by because in a sense this p and x, or psi and x, are equal to minus a h bar, and the way you can solve it, which is pretty nice, is you define x to be a plus, right, I a dagger and I minus a dagger, sorry, a dagger, and the commutator of a and a dagger is equal to 1, and then you, so these are the so-called creation and annihilation operators, and you can basically, this allows you to diagonalize this Hamiltonian in order to get the eigenvalues, which are n plus 1/2. I mean, usually, you know, every course of functional analysis starts with this, and yeah, one cannot actually overstate the importance of that for us physicists. So now we take mu n of the inverse of this Hamiltonian, and this is given as 2 divided by 2n plus 1. And from that, it follows that this gamma n of H inverse converges. Okay, and basically we just, you know, plug this formula in for the Dixit trace. So the 1 over the logarithm of n, the sum of, you know, n equal to 0 to n minus 1 of mu of H inverse, which is basically, you know, 2 divided by 2n plus 1. And now you see that basically if you take the limit for n goes to infinity, this goes to 1. Okay, so the trace is also defined for that operator, which is very nice actually. Good. So this is basically what we call the Dixit trace. And again, you have, you know, of all these bounded operators in the Hilbert space, you have a subset which are the compact operators. And these compact operators, you take another subset, which are those that are infinitesimals of order 1, which means that as n goes to infinity, decays as n to the -1. And now for these operators, we want to trace. We wanted to define trace, which is not just the usual sum over all eigenvalues, but it's a little, but because this, this goes as it decays as 1 over n. If you take the sum decay, it diverges, worst case as logarithm, and the Dixmuir trace is a way to, subtract or, divide by this logarithm and thus have a trace. And it is called a trace because it's linear and it's cyclic and it's positive if the operator itself is positive. Okay, now let us come to something called, before I define anything else, I want to define what a pseudo-differential operator is. How many of you are familiar with the concept of pseudo-differential operators? Or if anyone is not familiar, can he please write, or she write in the chat, me, I'm not familiar. Okay. Perfect. That's so, okay, well, the point is, yeah, I'd rather have it that way than you're familiar and I'm boring you and telling you stuff that you already know. So given a k vector bundle E to M, with M being a compact n-dimensional manifold, let us denote gamma of E as the C infinity of M module corresponding to the smooth sections. Okay. A differential operator of rank M is a linear operator from gamma of M to gamma of M, and local coordinates of M, it can be written as, some differential operator. For example, I don't know, some different, so what is the most complicated? Well, I'm sure there's more complicated, but a relatively complicated but not trivial second order differential operator, linear differential operator, is given as alpha x of I j d dxi d dxj plus beta I d dxi plus yeah, this can also depend on x plus some function f of x, for example. This is a differential operator of second order. These, here you take the sum over I and j. Here you take the sum over I, right? And right, this is a differential operator of second order. And in general, n-dimensional, an n-order differential operator can be written as the linear combination of a alpha of x, some functions or some matrices in this case, minus I to the power of alpha dx alpha, where this can vary from dx1 to the alpha 1 to dxn to the alpha n, where this is a multi-index. Okay, so three-dimensional third order differential operator can be written as di, dj, dk in local coordinates, right? This is derivative, plus alpha ij di dj plus beta I di plus some function, okay? And this can be done, in order. Sometimes you put also a little bit of restriction on these coefficients. Especially in physics, you would like them to be C infinity and so on, but this is not that very important. Here we restrict ourselves to these coefficients as k times k matrices, because as you saw, for the first order, it's just a vector. For the two order, it's a 2 by 2 or n by n matrix and so on, okay? Of smooth functions on M, and alpha is unequal to 0 for some alpha, okay? So now you have a manifold, right? And now consider a vector on the cotangent space. So you have a manifold, you have a tangent space, which okay, you have a manifold, and let me draw a manifold. So a teacher of mine called Bertelmann, Reinhold Bertelmann. So maybe I can show you. So here's his book. It's called Anomalies in quantum field theory, an excellent book if you want to learn about differential geometry in general, actually. And he draws a manifold as he calls it a Schnuller, okay, which I don't know if it's basically in German, I think it's called the same. So it's basically this thing that children, suckle on to keep them quiet. And so a manifold can have, a very strange look. And as he writes it, it looks like a Schnuller. And then let's say you have here some sort of, here you have some spaces, whatever you want to cut them in. And now let's take this point X, and on this point you put a tangent space, a space consisting of all vectors that are tangent to this, on this point. And right, and to this space, the dual is the cotangent space, basically. In physics, sometimes, sorry, here J is missing. In physics, sometimes this is usually the momentum space, it's called. And so now you consider a vector psi, in this cotangent space, and the principal symbol I define as the leading term of this pseudo differential of this differential operator. Okay, what does that mean? Let's take the Laplace-Beltrami operator on a manifold, on a Riemannian manifold, right? So this is di dj. Let's even make it more simple. So minus delta ij di dj, right? So this is the delta function. This is 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so the delta, Kronecker delta. And so what is the principal symbol here? The principal symbol would be just delta ij, psi alpha, psi j. Okay, this is the principal symbol. The principal symbol is you look at a differential operator, of an n order differential operator. You take its leading term and you take the k times k matrix there and multiply it by some, vector in the cotangent space. Okay, and right, and here actually this is where interesting definitions come into place. Sorry, my thing is stuck. All right. Okay. So the differential operator P is called. So there are, you have differential operators: elliptic, hyperbolic, parabolic, and so on. And one which plays a fundamental role in differential geometry and in Riemannian geometry especially is called an elliptic differential operator. And an operator is called elliptic if its principal symbol is invertible for psi element T star of n, which is unequal to 0. What does it mean? That means, and perfect. I have here a very nice example. So these were all a little bit definitions. Let me give you a very concrete example. The Laplace-Beltrami operator that maps C infinity functions on a manifold to C infinity of a Riemannian manifold in local coordinates can be written as, the sum over mu nu, d square g mu nu, where g is the metric, right? The inverse metric actually, d square f dx nu plus the sum over a nu dx nu plus some function b. Of course, note that in general, in general, all these, functions can depend on x, of course, on the local coordinates. And the principal symbol here is you take the leading term, g mu nu, and you multiply it by psi mu, and this gives you psi squared, right? The norm of psi squared. Is that invertible? Yes, it is. If psi is unequal to 0, this is invertible. Hence, this Laplace-Beltrami operator on a Riemannian manifold is an elliptic operator. Okay, elliptic operator of second order, they call it. Okay, this is a bit, I can, let me tell you this maybe. So by using the symbol, an action of P on a local section U of a bundle can be written as this. So you apply U, the differential operator mu of x. U of x is a local section of this bundle. And this can be written as e to the power of the scalar product of psi of x, P of x psi, U hat of psi, where U hat is something similar like a Fourier transformation of of the u. And now we use this p of x psi to define what a pseudo differential operator is. This all sounds a little bit complicated probably, but for simplicity, let us take the trivial bundle over Rn of rank k, take R, and so yeah, actually we could do it for, okay, let's take the operator minus delta ij dxi dxj. We know, now this is an elliptic operator because delta I, so the principal symbol xi I xi j, sum over I and j, is unequal to 0 for xi unequal to 0, which means it's invertible. Okay, we know it's an elliptic operator. Maybe it's not that important to stress the elliptic point that much. But now what we also can do is we can apply this operator on some u of x, which can be written as e to the power of I psi x, so it's in yeah, let's say in dimensions, times so then this is u hat of xi dxi. Okay, this will give me xi squared u of xi. Why? Because u hat of xi is e to the minus xi times x, u of x. And now the point is, if I apply the Laplacian here, right? So the Laplacian here, I can do a partial integration, and assuming that you've, the case fast enough, I apply it on the e, and this gives me a xi squared, okay? So now we get the p. And basically the p tells me, so if I can prove that for this representation of the differential operator, this function p decays in such a way that if I apply the derivative with respect to x and the derivative with respect to xi on p of x xi, and it decays less equal than ck alpha beta times 1 over the mean value of xi to the power of m minus alpha, where alpha is here. So alpha here is, they're all multi-indices. I don't know if you're familiar or not, so it doesn't matter. Just take it as one index. If you can prove that, then you know that your original p is a pseudo differential operator of order n. Okay, pseudo differential operators are very important to define oscillatory integrals, Fourier transformation, all that. Basically, what does it mean to have a pseudo differential operator? You have a differential operator, you know its principal symbol. With that, you can calculate, in a sense, how fast it decays, right? Or how slow it decays, actually. And if you can prove that a differential operator satisfies a certain, boundedness criteria, then you say it is of order m. So if it decays, here as fast as m. I hope that was clear a little bit. And in the case of our operator xi squared, so we had the Laplacian as just minus delta ij di dj, right? With the minus here. And then we applied it to a function, right? So pi c, sorry, that was u of x. And now we have e to the I x psi u of xi. That was the result. And now this is our p of x psi. Now we take it and we put it here. dx beta, d psi alpha, p of x psi. And this, so first of all, what we instantly see, and I don't understand why I cannot go instantly back to this. So we instantly see that this function, pi of x psi, since it's just xi squared, it's not dependent on xi. So that means that beta can be equal to 0, or beta has doesn't play a role here at all. But the xi alpha plays a role, and basically I can differentiate it twice, okay? And then you can make this inequality. Okay, so basically, pseudo differential operator of order m is a differential operator that, you know, given in this weird, representation as this Fourier transformation. So with the P of x has a certain boundedness to it, okay? And as I said, you can define oscillatory integrals with that and a lot more, right? Okay, so that is a pseudo differential operator. A pseudo differential operator is just a differential operator that has a certain boundedness to it. Now, the last thing that I will define for today, and so we have three slides left, is the so-called Wojcicki residue. This will be also important in the sense, and this is the reason why I defined a pseudo differential operator. Because the Wojcicki residue is the unique trace on the algebra of pseudo differential operators of any order. So you take a pseudo differential operator, which is a differential operator with sort of decayness to it. So it has a decayness property, and of any order, and the Wojcicki trace is a unique trace of that. Now, for the exact definition, let M be an n-dimensional compact Riemannian manifold, okay? And let T be a pseudo differential operator of order minus n. So it decays, you know, as minus n, acting on sections of complex vector bundles. Its residue then is defined, so maybe forget this 1 over n, that's not important, as the internal trace, so trace over with respect to internal indices of sigma minus n of t d mu, where sigma is the principal symbol and the integral is taken over the unit cosphere that is defined as, you know, x and psi are element of the cotangent space of the manifold, with psi norm being equal to 1, and this is a subspace of the cotangent space of this manifold, and the measure is just dx and d psi. Okay, this sounds a little bit, maybe, you know, as we say in German, aus dem Himmel gegriffen, but it's actually not that abstract. You can actually very easily calculate with it in a certain sense. Actually, way easier than Dixit trace, because, well, in general, integrals are just easier than sums. I mean, don't quote me on this, but I think this is the way it is. Let's take, for example, powers of Laplacian on an n-dimensional flat torus Tn. We take the second order differential operator, which is just the Laplacian. Delta minus n half of order is of order minus n with principal symbol psi norm to the power of minus n, which is 1 on this co-unit sphere. Now, as a consequence, we just, you know, plug in this into the formula here. So the residue of delta is equal to 1 over n 2 pi to the power of n, right? And and now, okay, it doesn't have internal indices. For the moment, forget this trace, the internal indices trace. The principal symbol of that, since it's a Laplacian, and I basically always gave you an example as the Laplacian, if you may have noticed, the principal symbol of this Laplacian is basically just this psi to the power of minus n. And since we work on the co-unit sphere, this is 1, so you just have to integrate over dx d psi. Now, so dx over that is omega n, and then you do the integration again, and you get 2 pi to the power of n half divided by n times gamma of n half. Okay, whatever. So this is just a number. The other example is powers of Laplacian on an n-dimensional sphere. So delta to the minus n half is of order minus n, with principal symbol constant function 1 on s star Sn. And now the residual. I calculate the same thing. I have this principal symbol, which is again just the 1 function over dx d psi, and this gives me 2 pi to the power of n half divided by n gamma n half, where I used some nice identities. And this is equal to 2 divided by n factorial. And now the question to you, with what does that remind you of? Sorry. So, I mean, the point is, I didn't take those examples by chance. There was a reason why I took those examples, and namely the reason is that by calculating those, you see explicitly that you remember the Diximir trace, and the Diximir trace you had here gamma n divided by n, and for the sphere you had 2 divided by n factorial for the Diximir trace. Now for the Wojcicki residue we have the same result. Okay, and that is sort of one of the surprises in this. The examples I gave you, the Diximir trace and the Wojcicki residue coincide. And this is not a coincidence, although they coincide. There's a theorem by Kohn which says basically the Wojcicki residue and the Diximir trace coincide for any pseudo-differential operators of order -n. Okay. And now let M be an n-dimensional Riemannian manifold, T a pseudo-differential operator of order -n acting on sections of complex vector bundles. Then T on this Hilbert space of square integrable sections of complex vector bundles belong to the Diximir trace, to the infinitesimals of order 1, compact operators of order 1, and damn, I just recognized how I could prove something that I've been working on quite some time, actually. Okay, very good. And the trace, the trace is, so the Diximir trace is independent of omega, and the Diximir trace is equal to this Wojcicki residue. And the trace only depends on the conformal class of the metric on M. Okay. Now, just as a last remark, in a sense, why is that important? Now, you see, the point is, if I can relate this, to the trace of some operator, of the operator T, in a sense. Sorry. So if I can relate this to the trace of an operator T of this Diximir trace, then in a sense I don't need the integral. Okay, given an operator, I can calculate its Diximir trace. I know the Diximir trace corresponds to the Wojcicki residue, and thus already I have sort of in this corner of the world, I just have the operator, the algebra, and all that, and the eigenvalues. Okay, this is sort of purely algebraic and functional analysis. On the other side, I have geometry, and in a sense, this is sort of an important point. Sorry, I just want to see if I can. I need just what? Sorry, I'm a bit. Need some. Okay, let me see if I get a whiteboard. Right. Okay. So basically, what happened in general relativity, Einstein was able to relate. Let's put it with the cosmological constant minus. Okay, Einstein was able to relate, geometrical quantities. So you have a metric, right? You have the metric M and G. If this metric is curved, it has a Riemann tensor, a Ricci tensor. So a Riemann tensor is usually like that, and a Ricci tensor, and a Ricci scalar. Okay. And what Einstein was able to do is relate the geometrical side of a space-time or of a manifold, as mathematicians call it, with the energy content of this space-time. Basically, if you calculate this for very easy examples, what you get is the Newtonian approximation, which people used to understand as gravity, and now this has changed. And in a sense, this is what non-commutative geometry, in this perspective, does, is it replaces these integrals and these residues, which are given by integrals over the manifolds, by something which is purely algebraic and operational. okay? It's just about the operator algebra there. And this is sort of the key with which we will next time define, you know, define a spectral triple. And I will show you how out of an algebra, a Hilbert space, and a Dirac operator, using the Wojcicki residue and the Dixmuir trace and their equivalents, we can reconstruct geometry by simply having those three quantities that are non-geometrical. Okay. So yeah, that is basically it for today. I hope I didn't, so I mean, I was sure I will end a little bit earlier, but I know there is a lot of to take in, so I didn't want to, you know, do it more. I will upload the first two Ringvorlesungen on my homepage, so you can, you know, check them and recall all the information if you need to, so that next time, you know, we conquer the conspectral triples. And well, any questions so far? Well, if not, then I thank you for your attention, and we will see each other next week. Then thank you.
Thank you.
Thank you.
Thanks. Bye.
Bye.